Modern infrastructure depends on heavy machinery. To keep massive steel gears and pistons from grinding themselves into dust, engines require a constant supply of slick, highly durable petroleum lubricants. But the cost of that performance is high. When industrial oils leak or spill during extraction and transport, they leave behind toxic deposits in soil and water that can persist for decades. Biodegradable alternatives like soybean or corn oil exist, but using edible crops to lubricate machines creates a direct competition with the global food supply. Even when food security isn't the primary concern, raw vegetable oil is structurally fragile. Inside a high-heat engine, the molecules break apart, and in cold weather, the oil tends to solidify and freeze. The challenge is to find a non-edible plant source that can be chemically upgraded to handle the heat and pressure of a high-performance engine. Researchers at Usmanu Danfodio University in Nigeria recently published a study exploring a new candidate for this role. Their work focuses on turning a hardy, wild seed into a stable industrial fluid. The source is Sesbania herbacea. Because it is an unedible weed that grows in marginal soil, it doesn't displace food crops, making it a viable biological candidate for industrial use. To make this weed perform like a synthetic oil, researchers had to unlock the seeds and run the raw fats through a multi-stage chemical transformation. The seeds are first washed, dried in the shade for a week, and then milled down into a fine, workable powder. To extract the oil, the researchers use a soxhlet extractor with N-hexane. This solvent washes through the seed powder under heat, pulling the natural fats out of the plant matter. This process recovers exactly 20% of the seed's weight as a raw liquid oil. At this stage, the oil is still composed of heavy, unstable triglycerides. It's too thick for high-speed engines, so it requires a first chemical intervention called transesterification. The raw oil is mixed with methanol and a potassium hydroxide catalyst, then held at 60 degrees Celsius for 1 hour. This reaction separates the heavy glycerin from the lighter chains, resulting in a combustible fluid known as a methyl ester. While this produces a functional biodiesel, the fluid is still too thin to provide the protective film required for heavy-duty lubrication. To increase the viscosity and thermal stability, the researchers initiate a second, more aggressive chemical reaction. They take the newly created esters, heat them to 100 degrees Celsius, and introduce a crystal compound called trimethylolpropane, or TMP. The reaction with TMP locks the molecules into complex, stable, star-shaped esters that can better withstand mechanical shearing. As the mixture cools to room temperature, it transforms into a highly viscous biolubricant. The seed's original chemical flaws have been engineered away, leaving a synthesized fluid designed for the high-friction environment of an engine block. To see if this lab-grown fluid can actually replace traditional oil, it had to be measured against the ASTM D5 limits, the international benchmarks for industrial performance. The kinematic viscosity test returned a result of 51.20. This indicates the fluid is thick enough to prevent metal-on-metal wear while remaining fluid enough to circulate properly. In the viscosity index test, it scored 180. This proves the lubricant can endure significant temperature swings without its molecular structure thinning out or breaking down. The fluid also maintained its flow down to a pour point of -9.8 degrees Celsius, confirming it remains viable in cold climates, where raw vegetable oils would typically freeze. By meeting these benchmarks, the synthesized biolubricant demonstrated that it can match the specific mechanical performance of traditional petroleum. The researchers used FTIR scans to confirm that these physical properties were the result of a successful molecular transformation. On the resulting spectrum, the sharp peak at 1743 provides physical evidence of carbonyl group formation, indicating conversion to a stable lubricant. Further down, the wide depression at 3384 identifies OH bonds, confirming the chemical linkage with TMP is complete. This specific lab result suggests that the historic trade-off between industrial performance and environmental toxicity is a technical hurdle that can be addressed through targeted chemistry. By successfully converting an inedible weed into a high-spec industrial fluid, this research establishes a viable chemical pathway for developing biodegradable lubricants that do not compete with the world's food supply.
Submit your manuscript today.